So we're in this era now of these massive pre-trained language models.
Absolutely. The llama class models, the big players.
Exactly. And they're these incredible, powerful brains, right? These foundation models with just billions of parameters all tuned for general knowledge.
But that's the thing, it's general knowledge.
And the second you want to make it specific, to customize it for your job, whether that's niche medical questions or, I don't know, internal company docs.
You hit a wall, a very expensive wall.
A wall made of compute.
A raw made of compute, pure and simple. I mean, full fine-tuning, updating all those billions of weights is just ridiculously expensive.
Well, putting huge memory footprints, right?
Huge. Taking days or even weeks and requiring these dedicated racks of high-end GPUs. For, the vast majority of researchers or startups or even mid-sized companies, it's the scaling bottleneck right now.
So you have this perfect base model, but making it yours is just prohibitively complex.
We're all facing fine-tuning fatigue.
Exactly. And the industry, it's recognized this pain, which is why we've seen the rise of these parameter-efficient fine-tuning methods, or PEFTs. They're designed to find a shortcut. For today's deep dive, we're looking at a solution that doesn't just, improve on those shortcuts. It fundamentally shifts how we think about adapting these models entirely.
Okay, I'm intrigued.
We are diving into a game-changing paper on representation fine-tuning, or ReFT. And the mission here is to understand how this method manages to edit the model's internal thoughts, its ephemeral, in-the-moment computations.
Instead of its weights?
Instead of its actual weights, its permanent memory. And it does this to achieve, hyper-efficient fine-tuning.
And this is a radical conceptual shift because the efficiency claim that comes out of it is, it's staggering. The strongest version of this framework, they call it LoReFT, that's low-rank linear subspace ReFTT, is basically positioned as a direct drop-in replacement for all the SOTA PEFs we use today, like LoAF.
Okay, but what's the actual number?
Here's the jaw-dropper. This is what demands the deep dive. LoReFT gets state-of-the-art results on major benchmarks while being dramatically more efficient. We're talking about an increase of 15 times to 65 times more parameter efficient than standard LoRa.
15 to 65.
55 times. That's not an incremental improvement. That's a different category of efficiency. That's the difference between needing, $100,000 of specialized hardware versus something you could maybe run under your desk.
It's a fundamental shift in the economics of customization.
That is the promise we are unpacking today, how they got this insane efficiency and this amazing performance just by deciding to edit the mind, not the memory, of the LLM. Okay, let's really break down this whole fine-tuning fatigue thing and nail down the cost. We know it's expensive. But say you've got a massive model like Llama 13B, and you only have a small, very specific data set, maybe 10,000 examples of regulatory compliance text or something.
A very common use case. Right. Updating all 13 billion weights for that is just computationally impossible for most people.
It's not just the memory cost during the training run itself, which is substantial. You need huge GPU VRAM to hold the model, the optimizer states, the gradients, all of it.
Sure.
It's also the long-term logistical cost. You end up with a huge, unique checkpoint, a whole new copy of the Llama 13B model for every single one of those small tasks.
So if you have 10 different tasks, you have 10 massive model files to store and serve.
It's a nightmare. And that's exactly why the community became so reliant on PEFTs, the parameter-efficient fine-tuning methods. They were designed to solve this exact logistical and computational headache by only training a tiny fraction of the parameters.
And before this new ReFT paper came along, PEFTs pretty much fell into 3 major camps, right? Based on how they did that limited update?
That's right. The first category, sort of the classic approach, is the adapter-based methods.
Okay.
These involve surgically inserting small, new modules, usually some fully connected layers, in between the frozen layers of the base model.
So you freeze the big original model and just train these little plug-in modules you've added.
Precisely.
I remember adapters. They were really popular for a while. It feels intuitive, like plugging in a small customization chip. But what was the trade-off? Why did they fall out of favor?
The main unavoidable drawback is inference time. Since these are totally new components, new layers that weren't part of the original math, you can't just merge them back into the base model weights.
Oh.
So every single time the model runs, it has to execute these extra adapter layers, and that imposes an additional computational burden.
It adds latency.
Which is a killer when you're serving millions of requests and every millisecond of lag costs you money.
Which brings us to the current champion, right? The one that solved that latency problem. LoRa, low-rank adaptation, and its cousin, Dora.
Exactly. LoRa and Dora really earned their state-of-the-art status because they tackle the weight updating problem directly. They use some clever math, these low-rank matrices, to approximate the necessary weight updates.
So instead of calculating the full, massive change needed for a weight matrix,
They calculate two much smaller matrices, usually called A and B, whose product approximates that big change.
and the absolute genius of LoRa is that once you're done training, you can just mathematically merge those tiny low-rank matrices back into the original big weight matrices.
Correct. Your base model weight matrix W just becomes W plus the product of A and B. After you merge them, there's no extra computation.
Meaning zero inference overhead.
Zero. That's why LoRa completely dominated the scene. It's clean, it's efficient to train, and it's totally silent in production.
Okay, so then the third major category is the prompt-based methods. These feel like the most hands-off since they don't even touch the model structure.
Right, they just tune these soft tokens, which are just specialized embeddings that you add as a prefix to your input. You train the values of those soft token embeddings while the main LM stays completely frozen.
It feels like a very advanced form of prompt engineering, you know?
It does. But empirically, these methods often just deliver suboptimal performance compared to the weight-based PEFTs. And they also carry a pretty significant scaling inference overhead because you're feeding these big specialized prompt embeddings through the whole system every single time.
So, okay, we've got this spectrum. Adapters work well, but add latency. LoRa works well and merges cleanly, but it's still modifying the physical wiring, the weights. And prompt-based methods, they kind of underperform and still add latency.
But the key thread here is that they are all, in some way, focused on permanent memory modification.
Right.
And that's the conceptual gap that ReFT is designed to exploit. LoRa and Dora are fundamentally about modifying weights, the neural connections themselves.
Yeah.
But what has, a decade of interpretability research been telling us?
What has it been telling us?
It shows that the model's representations, those hidden states, the thought vectors flowing from layer to layer, are incredibly rich. They encode complex semantic information in real time as the model processes the input. Things like linguistic features, logical steps, attributes of entities.
Wait, hold on. Let me make sure I'm getting the depth of this pivot. So instead of changing the permanent physical wiring, the billions of frozen weights in the brain, the core idea is that we should be injecting information directly into the instantaneous thought stream,
That's it.
the hidden representations that flow through that wiring.
That is the core hypothesis of ReFT. If these representations are the functional operating space where all the meaning and context are encoded, then manipulating those representations directly might be a far more powerful, more surgical, and crucially, a much more parameter-efficient way to steer the model, rather than just tweaking billions of underlying connections with low-rank matrices.
So we're bypassing the structural change and going straight to steering the computation itself.
It's like a form of surgical, non-invasive thought control. It's a complete philosophical shift in how we approach adaptation.
Okay, this shift from persistent memory, the weights, to ephemeral computation, the hidden states, is what makes this so exciting. Let's go back to that analogy we started with, just to ground this.
Let's do it. So your pre-trained large language model is that sophisticated high-performance race car engine, a finely tuned V12, billions of frozen parameters. Runs perfectly, but it's generalized.
Right. And traditional fine-tuning would be like tearing that V12 apart, changing every single bolt and valve to make it perfect for, say, a rally track.
An expensive, time-consuming overhaul.
Then LoRa is the cleverer way. Maybe you're just replacing a few key bolts with these custom low-rank ones, which is great because they merge back in cleanly.
Right. But LoReFT isn't touching the engine components at all. The engine stays frozen. Instead, LoReFT is like installing a tiny, task-specific, programmable chip.
A chip that does what?
It subtly alters the fuel air mixture, the combustion process itself, the instantaneous action of the engine to optimize its output for a specific, rainy, tight-cornered track. It changes the behavior without changing the structure.
The intervention is applied not to the model structure, but to the flow of information, the hidden representation, the H-vector as it passes between layers. So how do they actually do that? How do they implement the steering?
We have to start with the research that inspired it. Because LoReFT isn't just some arbitrary invention. It's deeply rooted in prior work on model interpretability, specifically something called distributed interchange intervention, or DII.
Okay, can you walk us through DII in a bit more detail?
Sure. So DII was developed by interpretability researchers to test causal hypotheses about how LMs process information. The core idea was causal abstraction, trying to find the minimal set of neural activity that's responsible for a specific high-level behavior.
Minimal set of activity.
Right. They hypothesized that specific human interpretable concepts, like, say, the number of a subject, singular versus plural, or the gender of an entity, aren't encoded by a single neuron. They're distributed across a linear subspace within the model's big representation vector.
So if the representation vector H is thousands of dimensions long, they were saying that maybe just 8 or 16 of those dimensions, combined in a specific way, controlled the concept of, I don't know, time frame or animacy.
Precisely. And they found that if they changed the representation in that specific narrow linear subspace, they could causally change the model's behavior related to that concept, like flipping a sentence from plural to singular without messing up anything else.
So they were basically finding the exact low-dimensional dial inside the model that controls one abstract feature. And they realized they could just turn that dial without rebuilding the whole dashboard.
Yes. And ReFT, specifically LoReFT, takes that realization and just operationalizes it for fine-tuning. Instead of just analyzing where a concept is encoded, they learn the subspace that's necessary to encode the desired task behavior. They learn the abstract space that dictates how to answer instructions or how to do common sense reasoning.
That makes a lot of sense. So you're learning the coordinates of the steering dial instead of just observing it. Okay, so how does LoReFT mathematically do this? How does it implement this targeted editing?
It starts with the hidden representation, H. The intervention wants to calculate a small edit vector, which is called delta, and then add it to H. So you get a new steered representation, H prime, which is just H plus delta. The key is that LoReFT restricts this edit vector, delta, to make sure it only lies within an r-dimensional linear subspace.
R-dimensional.
Right, and that subspace is determined by the rows of a learned low-rank projection matrix, which they call R.
So R is the learned blueprint for the thought dial. And because R is low rank, it only has a tiny number of rows, right?
Exactly. That low-rank R is incredibly small, often just 4 or 8 or 16. The total learned parameters, phi, just consist of that projection matrix R, plus a linear projection matrix W and a bias vector B. The base LM parameters, totally frozen.
So what's the actual process?
The process is, first the current representation H is calculated. Then the learned matrices W and B are used to calculate an initial edit signal based on H. You can think of this as the raw new task instruction. But then, and this is the critical part, this raw signal gets projected by the matrix R. And that function ensures the final edit vector, delta, is restricted only to that specific learned low-rank subspace that's defined by R.
So that's the key difference. In LoRa, you're learning the low-rank updates A and B that apply to the big weight matrix W. Here, you're learning the low-rank projection matrix R that applies to the representation vector H. It's like a filter or a focusing lens.
Precisely. LoRa modifies the memory, forcing the model to re-encode the task knowledge into its neural connections. LoReFT modifies the instantaneous calculation, inserting the task knowledge directly into the semantic thought stream.
Now, they also talk about an ablation, ReFT, which sounds like it's related but more efficient. What does ReFT get rid of, and what does that tell us?
ReFT is important because it simplifies the full LoReFT equation. It removes two constraints, the orthogonality constraint on the projection matrix R, and a difference operation that just makes LoReFT a bit more stable.
And when you simplify it like that,
when you look at the simplified equation for dire effect, it conceptually looks a lot like the math of LoRa's, but applied directly to the residual stream to the hidden states.
So it's like you're taking the math of LoRa, which updates the weights, but instead of applying that structure to the weights, you're applying a similar structure directly to the stream of activations flowing between layers.
That's exactly the right way to visualize it. ReFT trades a tiny bit of performance compared to the full LoReFT for, increased simplicity and computational efficiency. But the empirical evidence really suggests that keeping the orthogonality constraint in LoReFT is what boosts performance significantly.
Wait, why is orthogonality so important? What's the benefit of forcing those linear dimensions to be perpendicular to each other?
Well, the hypothesis is that orthogonality minimizes interference. If you're trying to learn multiple different high-level features for a task, say, understanding the context of a medical chart and also producing a concise summary, you want the learned subspaces for those two features to be as independent as possible.
So they don't step on each other's toes.
Exactly. If the subspaces are orthogonal, the learned features don't overlap or fight for the same dimensions in the representation space. This lets the model use the learned intervention arm more cleanly, and that leads to better generalization and stronger results. It's why LoReFT usually beats DRFT even with the same number of parameters. It's all about disentangling the learned abilities.
That makes perfect sense. It's like making sure your puzzle pieces only fit one way so they don't muddy the waters for the other pieces.
Yeah.
Okay, the technical side is clear now. LoReFT is this surgical, low-rank intervention on the thought stream, and it comes from this interpretability research. But the real test for any new PEFT method is, can you actually deploy it? How does it stack up against LoReF? We've heard the headline claim 15 to 65 times more parameter efficient. Let's dive into the specifics of that efficiency punch.
The scale of the parameter reduction it's
Yep.
really staggering, and it's important to appreciate the context here. The goal is always to minimize the number of trainable parameters relative to the base model size, right? Because that directly impacts your VRAM usage during training, your checkpoint storage size, and ultimately how agile you can be with deployment.
So let's take the Llama 7B models as our baseline. LoRa, which we already think of as hyper-efficient, typically uses around, 0.8% of the base model's total parameters?
Right. And while 0.8% sounds tiny, on a 7 billion parameter model, you're still training tens of millions of parameters.
Yeah.
You still need a beefy GPU, often 24 gigs of VRAM or more, just to handle the model weights, the optimizer, and all the gradients.
Okay, so what does LoRa do to that percentage?
The change is dramatic. On the same Llama 7B models, LoReF uses a minuscule 0.031% of the base model's parameters.
0.031.
Yeah, think about that. They are reducing the trainable parameter count by a factor of 25 just on the 7B model. And when they scale this up to the Llama 3 8B model, LoRa uses 0.700%, but LoReFT slashes that down to 0.0026%.
That is where the 15x to 65x efficiency claim comes from. That's a huge logistical win. In practical terms, this means way less VRAM needed during training. You might be able to train a model that previously needed an 80 gig GPU on a consumer 48 gig GPU.
And shorter training times. And critically, much faster experimentation cycles.
But okay, here's the critical question. If LoReFT is using vastly fewer parameters, we're talking thousands instead of millions, doesn't it just take a catastrophic hit on performance?
That's what you'd expect, right?
It's exactly what I was thinking. This sounds too good to be true. Where's the patch? Is the model just fundamentally worse than a LoRaTune version?
Now, what's so fascinating is that it consistently isn't. Despite that minimal parameter count, the surgical targeted nature of the representation intervention seems to be so effective that LoReF consistently achieves comparable, or in many key cases, superior performance to state-of-the-art methods like LoRa and DORA.
So this is the paper's core finding.
It's the core scientific finding. The right type of parameter modification, this highly targeted abstract subspace modification, is far more valuable than the sheer quantity of neural connections you update.
Okay, so performance is on par or better, with 15 to 65 times fewer parameters. That sounds like a decisive win for training and storage. But we have to talk about the other side of deployment. Inference overhead.
Right.
LoRa and DORA can be merged, meaning zero overhead. ReFT, because it's actively intervening on the computation, it has to have a runtime cost.
That is the one critical trade-off, and the authors are very transparent about it. Since ReFT involves running a small, learned computation during the forward pass to modify the representation cache, it can't achieve that absolute zero overhead of a merged LoRa. But they manage this overhead very strategically.
How do they manage it? Is it being applied to every single layer and every single token? Because if it is, we're right back to that old adapter latency problem.
No, and that's the ingenious part. They focus the interventions only on a fixed number of prefix and suffix positions in the input prompt.
A fixed number?
Yeah, they only tune which layers to intervene on, and then the number of prefix tokens, B, and suffix tokens, S, to intervene on. So you might only intervene on, say, the first 10 tokens and the last 10 tokens of the prompt.
So if I feed a 10,000 token input into the LLM, the model only incurs the extra computational cost for those 20 specific tokens.
Exactly. And this is key, because the number of positions you edit is fixed. It does not scale with the prompt length. LoReFT imposes only a fixed additional inference cost. This makes it incredibly efficient for long context scenarios compared to older adapter methods that apply their modules to every token, which makes their costs go up linearly with the prompt length.
That's a fundamental distinction. If you're feeding a massive 4,000 token document into the model for a summary, that fixed overhead is probably negligible. But let me push back on that. You say the overhead is minimal, but for applications that need near real-time single-token generation like autocomplete or a rapid-fire chatbot, wouldn't any overhead, even 0.05 seconds, be a non-starter compared to a merged LoRa?
That is a fair and important point. For absolute lowest latency in short output scenarios, especially if you're bottlenecked by serving a massive volume of requests, LoRa's zero overhead is still superior. The authors acknowledge this. But for most applications where the user is submitting a complex instruction or a long context prompt, which is, increasingly the norm for enterprise LLM use, that trade-off shifts dramatically in favor of ReFT.
Can we quantify that? Do we have hard numbers on the overhead?
We do. The empirical overhead is reported as minimal. For instance, if you intervene across 10 layers with a rank of 8 on a Llama Way 17B model, the additional generation time for a fixed output of 256 tokens is roughly 0.05 seconds.
Okay, so a small fixed cost.
A small fixed cost. For that 256 token output, the added latency is tiny. But if the prompt was 8,000 tokens long, other adapter methods would have incurred a substantial, maybe multi-second overhead. LoReFT is still at 0.05 seconds.
So the calculus is clear. If training efficiency, tiny checkpoint size, and long context serving are your top priorities, LoReFT is the new champion. If absolute zero latency in short context scenarios is your non-negotiable requirement, LoRa still has the edge. That's a very clear architectural choice for developers to make.
All right, now that we get the tech and the efficiency metrics, let's look at where this thing actually delivers on performance. This isn't just a theoretical win. LoReFT is setting new state-of-the-art results in some really critical domains. Let's start with common sense reasoning, which is notoriously difficult.
Common sense reasoning is a perfect stress test for any fine-tuning method because it requires this generalized knowledge to be applied correctly across all these different scenarios. The authors actually created a major benchmark, Common Sense 170K, which combines 8 different tasks.
8 different tasks, like what?
BoolQ, PQA, CQ, Hellaswag, 10 grand, RRCE, RRCC, and OBQA. A real gauntlet. If a method wins here, it suggests really strong generalizable adaptation.
So how did LoReFT do against the champions LoRa or Dora on these reasoning challenges? It consistently outperformed all the other PEFTs across the Llama family, the 7B, 13B, Llama 2 7B, and even the new Llama 3 8B. On the Llama 3 8B, for example, LoReFT hit an average accuracy of 86.6% across those 8 tasks. That surpassed Dora's 85.2% and the other methods by even bigger margins.
That difference, 1.4% improvement on a combined benchmark, it might sound small, but in the LLM SOTA landscape, that's a pretty big deal. What does moving from 85.2% to 86.6% accuracy on common sense reasoning actually feel like to a user?
It feels like reliability. It means fewer times the model misses an obvious logical leap, fewer times it makes an elementary mistake because of conflicting premises. It's just a more robust application of real-world knowledge. It shows that by editing the thought process in that targeted way, you get better overall generalization than by modifying the fixed neural connections. The model learns to steer its existing knowledge more effectively.
Okay, let's move to one of the most practical, high-value use cases. Instruction following in chat models. This is what everyone is building today.
This is where the efficiency benefits really become tangible. They tested this by training LoReFT on Llama 2 7B, using the ultra-feedback dataset, which is a really high-quality, large-scale instruction dataset.
And the results here were kind of shocking, weren't they?
They absolutely were. Not only did LoReFT comfortably outperform existing PEFTs like LoRaS and RED, but the instruction-tuned LoReFT model also outperformed full-parameter fine-tuning on the same Llama 2 7B base.
Wait, let me make sure I understand the scale of that claim. The kitchen sink approach, the one that updates every single weight and takes all that compute, was demonstrably worse than the surgical approach that only updates, what, less than 1/3 of 1% of the parameters?
That's the stunning conclusion. The hypothesis is that updating every single parameter, even with small learning rates, can lead to some degree of catastrophic forgetting, or at least it can pollute the base model's core generalized knowledge. LoReFT, by freezing the core engine and only adding these tiny focused steering vectors, avoids that pollution. It finds the minimal necessary intervention to unlock the instruction following ability without damaging the generalized knowledge it already has.
Which suggests that the crucial information to switch a model from base mode to chat assistant mode lives mostly in those steering vectors, not the bulk of the weights. And we have to talk about the footprint again here.
Oh yeah. The instruction-tuned ReFT weights are tiny. We're talking less than 1 millib on disk.
Less than a megabyte.
It's revolutionary. You could package and distribute a fully instruction-tuned adapter that delivers near GPT 3.5 quality performance as an email attachment. Or update a deployed edge device over a cellular connection in seconds. It completely changes the conversation around model distribution and personalization.
They even stress tested this in low resource settings, right?
They did. They showed that even when they cut the training data way down to only 1,000 examples, a tiny fraction of the standard data set, or when they have the parameter count by using an even smaller rank, LoReFT still outperformed the other PFTs. It proves how well it can squeeze maximum utility out of minimal resources.
And what about on more traditional, smaller NLU tasks? Does it only work on big decoder models?
They cover that too. They tested ReFT methods on the GLUE benchmark using smaller encoder-only models like Roberta Base and Roberta Large, and it confirmed that representation editing works well across different model architectures and scales. It's not just a llama trick. LoReFT achieved comparable performance to the best previous method when parameter counts were matched, showing it has universal applicability.
Okay, we've established it's widely applicable and super efficient. But we have to be honest about the limitations. Was there any area where this hyper-efficient method kind of struggled?
Yes, there was one defined area of weakness: arithmetic reasoning. Specifically on hard tasks that require numerical solving, like Aqua, GSM-8K, and SVN-8K, LoReFT struggled a bit compared to LoRa and some of the adapter-based methods. It still beat prompt tuning, but it wasn't the top performer here.
And since this is a deep dive, we need to understand why. What's the hypothesis for this dip in performance on math problems?
The authors give a really compelling analysis. They suspect it's because these tasks critically require chain of thought, or PERT steps. And COT means much longer, multi-step, sequential reasoning outputs. But remember, LoReFT is optimized by intervening primarily on the prefix and suffix of the input. It's a fixed, localized intervention.
I see the limitation now. If the complex reasoning process is, say, 50 steps long, the scaring signal you applied to the first 10 tokens might have just dissipated or become irrelevant by the time the model is generating step 30 of the calculation.
That's exactly it. The effect of that fixed, input-based intervention might just wear off over the long, complex generation steps needed for multi-step arithmetic. This suggests a current limitation. For tasks that require extremely long, unbounded reasoning outputs, especially those demanding precise sequential calculation, like complex math, the fixed intervention may not be enough to sustain the steering effect.
That's a critical structural limitation. It means developers can't just blindly throw LoReFT at every single problem. If you're building a multi-step math solver, you might still need to consider a different PEFT that either modifies the weights persistently, like LoRa, or applies adapters continuously through the whole generation.
Correct. It highlights that your choice of fine-tuning method has to align with the structure of your task specifically, whether you need to steer just the initial thought process or you need sustained control throughout a lengthy generation.
So we have this method that's unbelievably efficient and widely applicable, but with this specific identifiable weakness in long-form reasoning. The authors also point out some limitations they had, like mostly focusing on the llama family. We still need to see how ReFT performs on other foundation models or, on multimodal systems like vision language models.
That generalizability work is definitely the next step. And they also acknowledge that the hyperparameter search space for ReFT, deciding which layers to intervene on, which positions, what rank to use, is still really large. For widespread adoption, automating that search will be crucial to make it easy for everyone to use.
So you don't have to manually tune which layers of the model's brain need the search.
Exactly. But the real payoff of this approach, beyond just the efficiency, is the interpretability angle.
Yeah.
ReFT didn't just appear out of nowhere for speed, it grew directly out of that DII and causal abstraction research. It's applied AI alignment.
It's a perfect feedback loop between interpretability and capability.
It is. ReFT's success shows that generalized model steering doesn't just need to be analyzed after the fact. It can be learned and applied in this highly targeted way.
So we're not just observing the brain, we're learning to write software for the brain's internal OS.
Precisely. And the fact that a tiny linear subspace, distributed across just a handful of neurons, can achieve generalized control over these vast, complex behaviors like instruction following, that fundamentally challenges a lot of existing interpretability work. Many researchers try to interpret individual neurons, like this neuron fires for dogs.
Right.
ReFT's success suggests a different picture, that neurons play varied, contextual roles, and the complex learned behavior is encoded not in a single neuron, but across an abstract linear subspace that is orthogonal to other learned abilities.
That's a huge insight for AI safety and alignment. But let's get to the most surprising results, the capability experiments that really show the power of these tiny vectors. Let's talk about memorization power.
These experiments were designed to just push the boundaries of how much specific information one tiny intervention could actually encode. They used the absolute minimal intervention, a simplified rank 1 LoReFT. On Llama 7B, that's only about 4,097 trainable parameters.
And just over 4,000 parameters,
Yeah.
a microscopic adjustment.
And they trained this microscopic adjustment to just remember a massive sequence. They chose the beginning of Alice's Adventures in Wonderland, and they found that this single tiny vector could correctly recover sequences up to 2,048 tokens long across most layers.
I have to just pause on that. 4,097 parameters can memorize a continuous stream of 2,048 tokens. The amount of information storage there is just disproportionately massive compared to the size of the modification. That vector is what, 17 kilobytes of data on disk? And it's acting as a temporary high-fidelity memory bank for a huge amount of text.
And they took it even further. They tested its ability to encode an arbitrary code book, a mapping of random input IDs to random output tokens, basically training it to be an index lookup table. The same rank 1 intervention could reliably memorize a codebook of up to 256 random input-output pairs with near-perfect recall in some layers.
That capability tells us so much about the model's internal mechanics. What does this suggest about how that low-rank projection matrix R is working?
It suggests that the projection R is incredibly effective at disentangling superpositioned information. In large LLMs, multiple concepts are often compressed or superpositioned into the same small set of neural activity. The ReFT intervention seems to act like this highly specialized index, effectively separating the base model's generalized knowledge from the new specific memory, allowing it to act as a simple index-based storage system.
That alone opens doors for incredibly lightweight knowledge injection. But the next experiment, multitask composition, might be the most exciting for system design. Tell me about the German sentence completion and instruction following puzzle pieces.
This is a direct empirical benefit of that linear subspace approach and the orthogonality we talked about. They treated ReFTs like composable software plugins.
Okay.
They trained one orthogonal subspace, a ranked 4 ReFT, for one specific task. German sentence completion. Separately, in a totally different training run, they trained a second orthogonal subspace for complex instruction following using the ultrafeedback data.
So, two distinct specialized abilities encoded in two different tiny orthogonal vectors.
Exactly. And because they're orthogonal, they shouldn't interfere with each other. So then came the test. At inference time, they combined them. They plugged both puzzle pieces into the model at the same time.
And the result?
The Llama model was able to produce instruction-following responses in German.
Wow.
They didn't have to train a specific, specialized German instruction-following model, which would require massive, unique German chat data sets and a ton of compute. They just composed the English instruction-following module with the German language module they trained separately.
That demonstrates such a powerful, interpretable form of compositional learning. You can just plug and play abilities into an LLM using these tiny vectors. You train the language capability once, the reasoning capability once, and then you linearly compose them into an entirely new model variant. That's the definition of modularity.
It's a compelling argument for the future of LLM software development. Instead of monolithic models, you can imagine a base model running a library of hundreds of these tiny, composable ReFT vectors, each one unlocking a different language or domain or persona.
And finally, let's circle back to the rapid safety adaptation. This feels so relevant to modern deployment challenges, the GUI-2 experiment.
This one really demonstrated how lightweight and fast adaptation can be. They wanted to quickly make a standard Llama 2 chat model mimic the extremely safe, refusal-heavy style of the GUI-2 model. So they fine-tuned a rank 4 LoReF using an incredibly small data set, only 5 examples from GUI-2's completion.
5 examples, that's barely any data at all. How fast was it?
The training finished in just 30 seconds on a single A100 GPU.
30 seconds?
This incredibly lightweight training allowed the Llama model to successfully adopt GUI-2's refusal style and ethos. It's a demonstration of light and fast, highly specific adaptation for safety or ethos transfer. You can instantly personalize or update the model's personality with almost no compute.
That means deploying a brand new safety patch could be a matter of minutes, not days of retraining a huge model. This changes everything for continuous model maintenance and rapid response to emerging challenges. You could quickly align a model to specific ethical boundaries defined by an organization with almost no computational footprint.
So as we wrap up this deep dive into representation fine-tuning, LoReFT really leaves us with three defining pillars that are poised to reshape the future of LLM adaptation. First, efficiency. We're talking 15 to 65 times fewer parameters than LoRa, which dramatically democratizes access to fine-tuning.
Second, power. LoReFT gets state-of-the-art performance on critical, complex tasks like common sense reasoning and instruction following, even beating full fine-tuning in some key cases. It proves that less can genuinely be more, as long as that less is applied surgically.
And the third, and maybe the most transformative pillar, is interpretability. LoReFT is rooted in causal abstraction, giving us a cleaner, more abstract, and composable way to understand and control model behavior through these tiny orthogonal linear subspaces.
The memorable takeaways here for you, the listener, are crystal clear. The next frontier of LLM adaptation isn't just about low-rank approximations of weights, it's about highly targeted surgical representation editing. And the weights of a trained, task-specific model can now be compressed down to literally less than 1 megabyte. That is revolutionary for edge deployment and just rapid sharing.
And remember the inference discussion. LoReFT's fixed overhead, because it doesn't scale with context length, makes it super attractive for serving use cases that involve huge input prompts, which is rapidly becoming the standard in enterprise AI.
This whole journey, from editing fixed weights to editing these ephemeral thought vectors, it really changes how we see the massive redundancy that's built into these models. If changing just a few thousand parameters in a specific linear subspace can steer a Llama 7B model toward such complex behavior, it raises an important provocative thought for you to mull over.
If the model's complex behavior can be steered by such a minimal intervention, what does this imply about the vast amount of unused frozen parameters, the billions of weights that remain untouched? Are those billions acting purely as a rich, generalized knowledge base that we simply need to point in the right direction? Does this method truly allow us to instantly personalize or update the specific style, ethics, or domain expertise of an LLM with minimal compute just by plugging in these tiny composable thought vectors? This capability fundamentally changes how we think about the deployment lifecycle, moving from updating massive models to simply installing minimal application-specific plugins. We strongly encourage you to look into the open-source library the researchers released, pyreft, to start exploring these targeted interventions yourself.